Light a match. Go ahead, picture it. That little wooden stick, you drag it across the strip and suddenly there's a flame. A tiny, dancing yellow-orange flame. Everybody's seen it 1,000 times. Nobody thinks twice about it. But let me ask you something that might ruin matches for you forever. Where does the flame come from? Not the spark. Not the friction. I mean the flame itself. That glowing, hot, flickering thing. What is it made of? Because it's not solid, it's not liquid. You can pass your hand through it if you're quick enough. So what are you looking at? Most people, if you press them, will say something like it's burning gas or it's heat made visible. And those answers aren't terrible, but they skip over the real thing that's happening, which is so much stranger and so much more beautiful than people realize. A flame is a region in space where molecules are coming apart. That's it. That's what you're watching. You are watching molecules being ripped into pieces. And in the act of coming apart, they release energy. Some of it is light. The glow you see is the visible signature of destruction at the molecular level. That yellow part of the flame, the part you'd draw if someone asked you to sketch a candle, that's not a gas glowing. That's tiny particles of solid carbon, fragments that haven't finished combusting yet, heated so hot that they incandesce. They glow for the exact same reason a coal in a fireplace glows, or the filament in a light bulb. Any solid object heated to about 1200 degrees Fahrenheit or above will start emitting visible light. The color tells you the temperature. Dull red is cooler, bright orange is hotter, white is hotter still. That yellow flame is incandescent soot, and it's somewhere around 2000 degrees Fahrenheit. The blue part at the base, where the flame meets the wick, that's where combustion is most efficient. There's no soot left because the carbon combined with oxygen so completely. You're seeing light emitted directly by the excited molecules themselves as they snap together into carbon dioxide and water. Hold that thought, because everything I want to talk about today starts right there with that little match flame, and it ends somewhere you probably didn't expect. See, I got to thinking one day about cremation, not in a morbid way, in a physics way. And somebody dies and the body goes into a furnace, a very hot furnace somewhere around 1800 degrees Fahrenheit, and after an hour or two, what comes out is a small box of powdery ash, a whole human being, reduced to maybe 5 or 6 pounds of calcium powder. And I thought, well, wait a minute. A person weighs, let's say, 150 pounds, and what comes out weighs 5. So where did the other 145 pounds go? That's not a metaphysical question. That's a bookkeeping question. That's a bookkeeping question. And in physics, we take bookkeeping very seriously. Every atom that was in that body has to be somewhere. Atoms don't vanish. They don't get used up. They don't evaporate into nothingness. So if 145 pounds of material is no longer in that box, it went somewhere specific. And I want to trace it. I want to follow every bit of it and tell you exactly where it ends up. Because when you do that, when you actually track the atoms, you learn something about fire, about chemistry, about the human body, and about what you even means, physically speaking, that I think is one of the most startling things in all of science. All right, let's start with what a human body actually is, atom by atom. Forget organs, forget tissues. I'm talking about raw ingredients. If you took a person apart, atom by atom, and sorted everything into little bins, here's roughly what you'd find. About 65% of the body's mass is oxygen. That surprises people. They think of oxygen as a gas, something you breathe. But oxygen is also the heaviest atom in water, and you are mostly water. Roughly 60% of your body weight is water, and in every water molecule, the oxygen atom accounts for about 89% of the mass. Hydrogen is light. Oxygen is what gives water its heft. Then about 18% is carbon. Carbon is the backbone of every organic molecule in your body, every protein, every fat, every strand of DNA. It's the structural girder that biological chemistry is built on, because carbon has this wonderful ability to form 4 bonds at once, linking to other carbons in long chains, branching networks, and rings. Your body is essentially a carbon framework decorated with other atoms. Then about 10% hydrogen, 3% nitrogen, 1% or so of calcium, almost all of it in your bones and teeth. And then tiny trace amounts of phosphorus, sulfur, sodium, potassium, iron, zinc, and a few dozen other elements in minuscule quantities. That's you. That's what you're made of. Oxygen, carbon, hydrogen, and nitrogen account for about 96% of your body mass. Just 4 elements doing nearly all the work. Now here is the critical part. These atoms are not floating around loosely. They're connected, they're bonded into molecules. The carbon is bonded to oxygen and hydrogen in fats and sugars and proteins. The hydrogen is bonded to oxygen in water molecules. The nitrogen is woven into amino acids and nucleic acids. Every one of these bonds represents stored energy. Think of each bond as a tiny compressed spring. It took energy to put that bond together, and that energy sits there, locked in the architecture of the molecule, waiting. When you eat food, what you're really doing is taking in molecules whose bonds hold energy, and your body shuffles those bonds around, releases some of that energy, and uses it to keep you warm, to move your muscles, to run your brain. But all those bonds, all that stored energy, it's still there in the body. Even after death, the molecular architecture is intact. The springs are still compressed. So when that body goes into the cremation furnace, what's about to happen is that all of those compressed springs are going to be released at once. Not gently, not gradually, the way metabolism does it over years. All at once. Violently. That's what the furnace does. Let's follow the chemistry step by step. The furnace heats the body to somewhere around 1800 degrees Fahrenheit, which is about 980 degrees Celsius. At that temperature, organic molecules cannot survive. They don't just get warm, they break. The thermal energy, the sheer vibration of the atoms at that temperature is enough to snap chemical bonds apart. Think about what heat actually is at the atomic level. Temperature is just a measure of how fast the atoms and molecules are jiggling. At room temperature, the molecules in your body are vibrating gently, stretching and bending, but the vibrations aren't violent enough to break the bonds holding them together. At 980 degrees Celsius, those vibrations become savage. The atoms are thrashing around so wildly that the bonds simply can't hold. Proteins unravel and shatter. Long fatty acid chains crack into fragments. DNA, that elegant double helix, falls to pieces. Sugars fragment. Every complex molecule in the body is torn down into simpler pieces. This first stage is called pyrolysis, the thermal decomposition of organic material. Pyrolysis, fire, lysis, breaking apart. But that's only the first act, because the furnace is full of air, and air is 21% oxygen gas, and those molecular fragments, those newly exposed carbon atoms and hydrogen atoms, are suddenly surrounded by eager oxygen molecules. And carbon has an enormous affinity for oxygen. Hydrogen does too. So what happens is immediate and fierce. The carbon atoms grab onto oxygen atoms and form carbon dioxide. 2 oxygens for every carbon, locked into a tight, stable, linear molecule. The hydrogen atoms grab onto oxygen atoms and form water, H2O, which at these temperatures is superheated steam. These are combustion reactions, and they are wildly exothermic, meaning they release energy, a lot of energy. Why? Because the bonds in carbon dioxide and water are much stronger, much more stable than the bonds in fats and proteins. In chemistry, we measure bond strength in terms of how much energy you need to pull the bond apart. The double bond between carbon and oxygen in carbon dioxide is ferociously strong. So when atoms rearrange from their old, relatively weak configuration into these new, more stable molecules, there's leftover energy. The atoms have settled into a lower energy state, and the difference comes flooding out, as heat, as light, as infrared radiation pouring off the furnace walls, as convection currents of scorching air. The furnace doesn't supply the energy for cremation. The body does. The furnace just provides the activation energy, the initial kick to get things started. After that, the reactions sustain themselves because they're releasing far more energy than they require. This is what fire is. Every fire, from a match to a forest blaze to a cremation furnace, it's atoms finding more stable partners and dumping the energy difference into the environment. Fire is atoms relaxing. In the cremation furnace, this happens on the scale of an entire human body. The carbon that was in your muscles, your skin, your organs, your brain, every gram of it, combines with oxygen and floats away as carbon dioxide gas, up the chimney, into the atmosphere. The hydrogen that was in your water, in your fats, in every organic molecule, combines with oxygen and leaves as water vapor. Steam, also up the chimney, into the air. The nitrogen, which was in your amino acids and DNA, mostly gets released as nitrogen gas, N2, which is already 78% of the atmosphere anyway. It just rejoins the air like a drop of water returning to the ocean. It's just small amounts of sulfur leave as sulfur dioxide. Trace minerals vaporize or oxidize. So let's do the accounting. That 145 pounds I asked about, it left as gas. Carbon dioxide, water vapor, nitrogen gas, and small amounts of other trace gases. It's all still there. Every atom. Not a single one was destroyed. They just changed partners. The carbon that used to be bonded to hydrogen in a fat molecule is now bonded to oxygen in a carbon dioxide molecule, drifting through the atmosphere. The hydrogen that used to be part of a protein is now part of a water molecule in a cloud somewhere. The nitrogen that spelled out your genetic code is now just part of the air someone else is breathing. And that box of ash, what's actually in it? Almost entirely calcium phosphate, the mineral component of bone. Hydroxyapatite is the technical name. It's a crystal, a mineral lattice of calcium, phosphorus, and oxygen. And it has an extremely high melting point, well over 1500 degrees Celsius. The cremation furnace, for all its fury, isn't quite hot enough to volatilize it. So the calcium and the phosphorus stay behind, along with tiny amounts of other minerals. Sodium, potassium, bit of magnesium, traces of iron and zinc. That powdery substance people keep in urns, what we call ashes. It's essentially ground up bone mineral. Everything else, every soft tissue, every organic molecule, every drop of water left the building as gas. And if we're being precise about energy, the chemical energy stored in a human body's organic molecules is roughly equivalent to about 110,000 kilocalories. That's enough energy to power a 100-watt light bulb for roughly 50 days. During cremation, nearly all of that stored chemical energy gets released as heat and radiated away. The furnace gets very hot, the flue gases carry thermal energy up the chimney, and eventually all of it dissipates into the environment. The energy doesn't vanish any more than the atoms do. It just spreads out, degrades into diffuse warmth, following the second law of thermodynamics toward ever greater entropy. The atoms are conserved, the energy is conserved. But the organization, the structure, the intricate arrangement, that's what's lost. And this is a deep point. The atoms in a living body and the atoms in the gases leaving the chimney are the same atoms. The total energy is the same. What's different is the arrangement. In the living body, those atoms were organized into fantastically specific structures. Proteins folded into exact shapes, DNA encoding billions of base pairs in precise sequences, cell membranes maintaining delicate chemical gradients. That organization represents low entropy, a state that's extraordinarily unlikely to arise by chance. Cremation doesn't reduce the number of atoms or the amount of energy. It increases the entropy. It takes a highly ordered arrangement and scatters it into a disordered one. And the second law of thermodynamics tells us that this direction, from order to disorder, from concentrated structure to diffuse simplicity, is the direction the universe overwhelmingly favors. You can unscramble an egg in principle. Nothing in the laws of physics forbids it. But the number of ways the atoms can be arranged in a scattered state vastly outnumbers the arrangements that constitute an intact egg. The universe doesn't conspire against order. It just has an awful lot more room for disorder. I want you to sit with the atomic picture for a moment, because it means something specific. The vast majority of what made up a human being, physically, is now distributed through the atmosphere, mixed into the air, and within days or weeks, those carbon dioxide molecules scatter across a wide area. Wind patterns carry them. Within months, they've spread across the hemisphere. Within a year or two, some have circled the entire planet. Some of that carbon dioxide will be absorbed by a tree, pulled in through the stomata of a leaf and used in photosynthesis to build new sugars, new cellulose, new wood. Some of that water vapor will fall as rain into a river, flow to the ocean, get drunk by a fish, evaporate back into a cloud. The atoms go on. They keep participating. They have no memory of where they've been, no loyalty to the pattern they were part of. They just follow the chemistry wherever it leads. This is not poetry. I want to be very precise about this. This is atomic bookkeeping. The law of conservation of mass is absolute, not approximately true. Not true most of the time. Absolute. Antoine Lavoisier demonstrated this in the 1780s with careful weighing experiments. He showed that in any chemical reaction, the total mass of the products exactly equals the total mass of the reactants. Nothing is created, nothing is destroyed, atoms shuffle. That's all. Cremation is a chemical reaction. A fast, hot, thorough one, but still just a rearrangement. Now let me push this one layer deeper. because there's something even more unsettling hiding inside this story. Those atoms that made up the body, the carbon, the oxygen, the hydrogen, they weren't yours to begin with. I don't mean that in some spiritual sense. I mean it literally. You ate them. Every atom in your body got there because you ate something, or drank something, or breathed something in. The carbon in your muscles came from food, plants that pulled it out of atmospheric carbon dioxide, or animals that ate those plants. The oxygen in your tissues came largely from the water you drank. The nitrogen in your DNA came from the protein in an egg or a piece of fish or a handful of beans. You assembled yourself, piece by piece, out of borrowed parts. And here's what makes it truly strange. While you're alive, you're constantly losing atoms and replacing them. You exhale carbon dioxide with every breath. That's carbon leaving. You sweat out water. You shed skin cells by the millions every day. You excrete waste. Careful isotope studies suggest that roughly 98% of the atoms in your body are replaced within the span of about a year. The specific numbers vary by tissue. The lining of your gut turns over in a few days. Red blood cells last about 4 months. Bone is slower, maybe 10 years for a full replacement. But the overall picture is clear. The body you had a year ago and the body you have today share almost none of the same physical atoms. You are like a wave in the ocean. The wave is real. It has shape, it moves, it carries energy, but the water passing through it is always different. The wave isn't a thing, it's a pattern that matter flows through. So when cremation disassembles the body, it's doing something that was already happening, just far faster. Metabolism is slow, controlled disassembly and reassembly. A few atoms out, a few atoms in, every second of every day. Cremation is total disassembly, with no reassembly on the other end. The atoms scatter, but they were always scattering. Death doesn't start the process of atoms leaving your body. Death just stops the process of new ones arriving to take their place. One more level down, we've been talking about atoms as if they're permanent little beads that get passed around forever. And for chemistry, that's exactly right. A carbon atom is a carbon atom. It doesn't wear out, it doesn't age, it doesn't degrade. But where did that carbon atom come from in the first place? The answer knocks people sideways. It was made in a star that burned and died long before our sun was born. Carbon is forged through a process called the triple alpha process, deep in the cores of red giant stars. 3 helium-4 nuclei, what physicists call alpha particles, have to fuse together under crushing temperature and pressure, around 100 million degrees Celsius, to form a single carbon-12 nucleus. 2 helium nuclei first fuse into an extremely unstable beryllium-8 nucleus, which survives for only about 10 to the minus 16 seconds before flying apart again. In that flicker of time, a third helium nucleus has to slam into it and stick. The odds are absurdly small. The whole process only works because of a very particular quantum mechanical resonance, an excited nuclear state of carbon-12 sitting at exactly the right energy level, predicted by Fred Hoyle in 1953, because he reasoned that without it, carbon couldn't exist in the universe in the quantities we observe. The prediction was later confirmed in a laboratory. So the carbon in your body is the product of a quantum coincidence happening inside a dying star billions of years before the Earth existed. The oxygen was made there too by carbon capturing one more helium nucleus in a further fusion step. The calcium in your bones was built up by even later stages of stellar fusion in more massive stars. And the iron in your blood, that came from the very last moments of a supergiant star's life. Iron is the end of the line for fusion. Fusing elements lighter than iron releases energy. Fusing iron or anything heavier absorbs energy. So when a massive star's core turns to iron, fusion stalls, gravity wins, the core collapses in a fraction of a second, and the star explodes as a supernova, one of the most violent events the universe is capable of producing. That explosion scatters all the freshly forged elements across light years of space. Billions of years later, some of that debris drifted into a new cloud, collapsed under gravity, and formed our solar system. The Earth condensed out of that rubble, and everything on Earth, including every atom in you, was part of that original stellar wreckage. So when that cremation furnace burns at 1800 degrees Fahrenheit, it feels tremendous to us. And it is hot for chemistry. But those atoms have already survived the interior of a star at 100 million degrees. They'd been through a supernova. They've drifted through the cold vacuum of interstellar space for millions of years. They were crushed and heated as the Earth formed, They've cycled through oceans and volcanoes and bacteria and dinosaurs and ice ages for 4.5 billion years. And then for a brief window, perhaps 70 or 80 years, some of them were arranged in the particular pattern that called itself a human being. Then the pattern dissolves, and they move on to the next thing. The furnace doesn't destroy anything. It can't. You would need nuclear reactions, the kind that happen inside stars or in particle accelerators, to actually transmute one element into another. Chemical fire can't touch the nucleus. It only rearranges the electrons, the outer social life of the atom. The atom's identity lives in its nucleus, in the count of protons, and that comes through cremation completely untouched. Carbon is still carbon, oxygen is still oxygen. They've merely changed addresses. And this is where the physics becomes, I'll say it, breathtaking. There is no sharp physical boundary between you and everything else. The atoms cycle through. The pattern is temporary. The matter is as old as the stars that forged it. You are not a fixed object. You are a process, a temporary, self-sustaining, brilliantly organized eddy in an ongoing flow of atoms that have been circulating for billions of years and will circulate for billions more. The flame of a cremation furnace is not an ending. It's a transition, a rapid redistribution. The carbon goes back to the carbon cycle. The water goes back to the water cycle. The nitrogen goes back to the nitrogen cycle. Every atom returns to the pool from which it was borrowed, and new patterns, new organisms, new configurations of matter will borrow those atoms again. Some already are. So the next time you light a match and watch that little flame dance on the end of the stick, remember what you're seeing. Atoms finding new partners, chemical bonds breaking and forming, stored energy spilling out as light. And you're seeing in miniature the very same process that would one day return every atom in your body to the wider world. The flame doesn't destroy, it rearranges. And the atoms were never yours to keep. They were just passing through. Pick up any object near you, a pencil, a cup, a leaf off a tree. Every atom in it was once part of something else entirely, and every atom in you was once part of something else too and will be again. If that thought makes you feel small, I understand. But I think it should make you feel enormous. You are made of the universe, not as a metaphor, as a measured, verified physical fact. And the universe has never once held still. Tell me this, knowing what you now know about where your atoms came from and where they'll go, does it change what the word you means to you?